Okay, then let's start with the stream. This will be a chemistry revision. Chemistry, whole of class 12. We are going to go in an order. I'm going to write that order now. First, we are going to do with D and F block elements. Second, we will go with coordination compounds. And third, we are going to start with organic chemistry, that is haloalkanes, haloarenes. Then alcohols, phenols, and ethers. Then we are going to go with amines. Then biomolecules. Then we are going to start with solutions. Then electrochemistry. Chemical kinetics. And finally, aldehydes, ketones, and ethers. This is a complete syllabus of class 12. We are going to go in this order. Now let's start with D and F block elements. I'm going to refer a specific notes and only write the most important points and most important questions. First, what are D block elements? D block elements, starting with first D block elements. What are D block elements? Elements in which added electrons enter into the n-1 d orbital are known as D block elements. Then next question, what are transition elements? Elements which possess partially filled d orbitals in ground state or ionic state are known as transition elements. Transition elements, they should possess a partially filled d orbital, and it can be either in their ground state or in their ionic state. What is the position of d block elements in the periodic table? Position, the position is between S and P blocks. There is one more reason. The first reason why transition elements or d block elements are called transition elements, because they have properties intermediate of S and P block. This is also one of the reason they are called transition elements. The transition elements have properties in between S and P block elements. They are properties intermediate of S and P block elements. They are present from group 3 to 12. Now, general electronic configuration of d block elements. It is noble gas, n minus 1, d 1 to 10, and ns 1 to 2. This is the general configuration of d block elements. This is the ground state configuration, hence there is a 10 here. Normally, if a completely filled d orbital, if an element has a completely filled d orbital in both ground state and ionic state, they are not considered as transition elements. For example, we have zinc. Zinc has a completely filled d orbital configuration, but it is still it's not considered a transition element, but it is studied along with them because it is a part of the d block elements. Let's see the exceptions later. Then in our chapter we are going to study most about the 3D series. So general electronic configuration of 3D series. It is argon 3D 1 to 10, 4s 1 to 2. This is a general configuration of 3D series. If you want to know how many series there are in d block elements, there are respectively 4 series. 3D series, that is from scandium 21 to zinc 30. Their general configuration is 3D 1 to 10, 4s 1 to 2. Then we have 4D series. This is from yttrium, that is 39, to cadmium 45, 48. Their configuration 4D10, 4D1 to 10, and 5s 1 to 2. Then we have 5D series, that is from lanthanum 57 to, we are not considering lanthanides which come between here. Lanthanum, comma, lanthanum is a part of the 5D series. It is not a part of the lanthanides. Then after lanthanum, we have hafnium 72 to mercury 80. Their configuration 5D1 to 10 and 6S1 to 2. Then the last series is 6D series from actinium 89 to 89, comma, rutherfordium 104 to roentgenium 111, 6D 1 to 10, 7S 1 to 2. There are another name for 3D series. It is called first transition series, second transition for 4D, and third for 5D, and finally fourth transition series for 6D. These are the names. The general configurations are very similar and easy to remember. The main general configuration for D block elements is n-1, D1 to 10, ns 1 to 2. Very simple and easy to remember. And we can take our time writing the 3D series and their elements and their configuration. We have, let's start in next page. We have scandium, atomic number 21, its configuration AR 3D14S2, titanium 22, argon 3D24S2, vanadium 23, argon 3D34S2, and chromium 24, argon 3D54S1, then manganese 25, argon 3D54S2, iron 26, argon 3D64S2, cobalt 27, argon 3D74S2, nickel 28, argon 3D8 4S2, copper 29, argon 3D10 4S1, zinc 30, argon 3D10 4S2. Here the configuration is very continuous except in two places. First place it is chromium, and second it is copper. In these two places, except these two places, all the remaining configurations are very continuous from scandium 1, 2, 3, 4, 5, 6 and till 10. The reason for this exception in chromium and copper is because instead of 3D4 4S1, our expected configuration of chromium is 3D4 4S2, but instead of that the actual configuration is 3D5 4S1. Here for copper the expected configuration is 3D9 4s2, but the actual configuration is 3d10 4s1. This exception comes because of fully filled and half filled stability. Fully filled and half filled stability. Here, instead of 3d4 and 4s2, if chromium has a configuration of 3d5 and 4s1, due to exchange energy and half filled stability, this configuration is more stable than this configuration. So chromium is uh, more likely to have this configuration because of its higher stability. The same reason comes for copper, and instead of half filled in chromium we saw half filled. In copper, the stability is due to fully filled configuration. Here 3d10 is a fully filled configuration which gives higher stability than 3d9 4s2. This is the reason. These are the two exceptions. Okay, now coming to one more important point, that's about some of the important points in 3D series. Now, for example, I told you about how some elements, even though they are d block elements, are studied with transition elements. They are not considered transition elements. They are zinc, cadmium, and mercury. They are not regarded as transition elements. These are, if you see, if I have written the series here from scandium to zinc here, cadmium, and mercury. These three are not regarded as transition elements. They are not regarded as transition elements because they have fully filled d orbital in both in ground state and common oxidation states. And common oxidation states. If we see here, zinc, it has 3d10 4s2 configuration. In a ground state, it has a completely filled d orbital. It is not partially filled, it is completely filled d orbital. It is completely filled d orbital. And even if we can have a question, even copper has a completely filled d orbital. So why can we consider copper as a transition element but zinc cannot be a transition element? That is because copper in its oxidation state, like Cu plus or Cu2 plus, in its oxidation state, it can have a incomplete d orbital. Because of that, it is considered a transition element. But zinc, zinc in its common oxidation states as well cannot have an incomplete d orbital. For example, in a incomplete, I mean, in a common oxidation state of zinc, that is zinc plus 2, the oxidation state is 3d10 4s0. Here as well, this is a common oxidation state. Here as well, it is completely filled d orbital 3d10. So because of that, in its ionic state as well, in its common oxidation state as well, zinc does not have incompletely filled d orbital. Because of that, we do not consider zinc as a transition element. The same reason is for cadmium and mercury as well. They have completely filled d orbitals. So if these zinc, cadmium, and mercury are not regarded as transition elements, why are they included under transition, or like they are studied with transition elements, or why are they included in d orbital elements? Is because They resemble the transition element in some properties. They have zinc, cadmium, and mercury have or share similarities in properties with transition elements, hence are studied with them. That is about zinc, cadmium, and mercury. I told you the reason why copper, silver, like even copper and silver and gold have completely filled d orbital in their ground states. But copper, silver, and gold have completely filled d orbital in ground state, but considered as transition elements because they have incomplete d shell in oxidation states. For example, in Cu2 plus, it has an oxidation state of 3d9. Ag2 plus, it has an oxidation state of 4d9. And Au2 plus, I mean 3 plus, it has an oxidation state of 5d8. Normally they have completely filled, but in their oxidation states here, they have incomplete d orbitals. Okay, there's a famous in-text question from NCERT. Let me write this question. On what ground can you say scandium with atomic number 21 is a transition element but zinc is not? This is a very famous question. Now, I already told why zinc is not a transition element. Now, why scandium is a transition element? Very common. I mean, very simple explanation. Scandium electronic configuration, if we write, it is argon 3d1 4s2. Here it has a 3d1. It is an incompletely filled d orbital. So obviously it is a transition element because it has incompletely filled d orbital. Okay. Now that's with the introduction part. Now coming to general properties of transition elements. General properties of transition elements. Now coming to metallic character of transition elements. All transition elements are metals. They show metallic character. Metallic character is because they can lose electrons and form cations. This is what generally all metals do. So all the transition metals can also do this, and hence they are showing metallic character. As for physical properties, these are very common. They have high tensile strength, ductility, that is, they can be uh, spread into thin wires, malleability, they can be hammered into thin sheets, they have high thermal and electrical conductivity, and there is also metallic luster. Most of them show metallic luster, and all of them except mercury are solids. All transition elements except mercury are solids. And as for their lattice structure, they have simple lattice structure, right? Their lattice structures are simple. Example, there is, they can be simple cubic, HCP, BCC, and CCP. And this is the one of the important point is this one: mercury is liquid in room temperature. Very easy to remember, very common information. Okay, there is a specific question or important point: the melting points and boiling points of transition metals are maximum at middle of each series. They are maximum at middle of each series. Why so? This is a question. Because of metallic bonding. What is the main reasons like metals have high boiling points and melting points is because in between individual metallic atoms there will be metallic bonding. This metallic bonding is facilitated through their valence electrons. So higher the number of valence electron, higher the metallic bonding. If we understand this concept, higher valence electrons, higher number of valence electron, higher the number of, higher the melting point, I mean higher the metallic bonding, and metallic bonding directly proportional to melting point and boiling point. So the question was, why is melting point of transition metals and maximum at middle of each series? We saw that the melting point and boiling point directly proportional to metallic bonding, and metallic bonding depends on the number of valence electron. So we can conclude, if they are saying that at the middle of each series there is highest melting and boiling point, we can conclude that at the middle of each series there will be the highest number of valence electrons, which is true if we see the configuration here. Coming to middle of the series, manganese has 3d5 electrons, meaning 5 unpaired electrons. These are 5 free electrons. The maximum number of unpaired valence electrons are seen at the middle of the series. at manganese. So that is the reason at middle of each series there will be highest number of melting point and boiling point. Or if I have to write it in a format, due to presence of more number of unpaired electrons in middle of each series, metallic bonding is very strong, involving unpaired electrons from both n minus 1 d orbital and ns orbitals in intermetallic bonding. Therefore, they have high melting and boiling points. And this is also the reason there is a general trend here. What this trend is, melting points and boiling points. Let's just conclude, right? Melting points for now. Melting points of transition metals increase up to d5, then decrease. This is the same reason unpaired electrons from scandium to manganese will increase from 1 to 5 electrons. The number of valence electrons will increase. But in case of from manganese to zinc, the unpaired electrons will keep on decreasing. This will reduce the number of unpaired electrons, and hence the metallic bonding also reduces and melting point also reduces. The number of unpaired electrons increases from up to d5. So metallic bonding becomes stronger and hence melting point becomes higher. After d5 configuration, pairing electrons takes place and number of unpaired electrons decreases. Metallic bonding becomes weaker and hence melting point decreases. Okay, we saw why mercury was a, we know that mercury is a liquid at room temperature. And not only mercury, mercury is liquid at room temperature. Now we have another information that zinc and cadmium are soft metals. That indicates that both of them have low melting points. They have low melting points. Why could be the case? We saw before, middle of the series, the melting point increases the most. That's the highest melting point at the middle of the series. But here now we are seeing, here we need to explain why low melting point. If we see, mercury, zinc and cadmium are at the end of their series and they have completely filled d orbitals. They have completely filled d orbitals. Hence, no unpaired electrons. All are paired electrons present. No unpaired electrons are present. Metallic bonding mainly depends on number of unpaired electrons. So if there are no unpaired electrons itself, then the metallic bonding will be greatly reduced. Due to the absence of unpaired electrons in mercury, zinc, and cadmium, metallic bonding is very weak. Therefore, their melting points are less. Hence, mercury exists as a liquid at room temperature, and zinc and cadmium are soft metals. Okay, there is one more trend in melting and boiling points. Let's remember the point first. Melting point of 3D series electrons, not elements, are less than 4D and 5D series. Why so? This is because the high enthalpy of atomization. What is enthalpy of atomization? That enthalpy of atomization is the heat required to convert metal lattice into individual atoms or free atoms. The 4D and 5D have 4D and 5D elements have high enthalpy of atomization. They have high enthalpy of atomization. That means we need more energy to convert these metals from lattice into individual atoms, and because of that they have higher melting point I'm from compared to 3D elements. Why melting point of 3D series is less than 4D and 5D series? Because 4D and 5D series have high enthalpy of atomization, which increases their melting point. And we can note a point here. Tungsten has the highest melting point of 3410 degrees Celsius, and mercury has the lowest melting point of minus 38 degrees Celsius. Minus 38 degrees Celsius. Okay, we saw that 4D and 5D series have high enthalpy of atomization. Why is it that transition elements exhibit higher enthalpies of atomization? Because large number of unpaired electrons in their atom, they have stronger interatomic interaction and hence stronger bonding between atoms, resulting in higher enthalpy of atomization. Enthalpy of atomization depends on number of unpaired electrons. This depends on higher metallic bonding. Enthalpy atomization, it is depending on number of unpaired electrons. Higher the number of unpaired electrons, higher the metallic bonding. Higher the metallic bonding, higher the enthalpy of atomization. Because transition metals have large number of unpaired electrons, they have higher metallic bonding, higher atomic interaction, interatomic interactions, and higher enthalpy of atomization. In 3D series, zinc has the lowest enthalpy of atomization. 3D series, zinc has lowest enthalpy of atomization, and the reason is quite simple. The extent of metallic bonding of an element decides the enthalpy of atomization. The more extensive the metallic bonding of an element, the more will be the enthalpy of atomization. In all transition metals except zinc with an electronic configuration of 3d10 4s2, there are some unpaired electrons that account for their stronger metallic bonding. Due to absence of these unpaired electrons, the interatomic electron bonding is the weakest in zinc, and as a result it has the least enthalpy of atomization. Basically there are no unpaired electrons in zinc, so hence it has the lowest interatomic interaction and lowest metallic bonding, and because of that it has the lowest enthalpy of atomization. Enthalpy of atomization is more in 4D and 5D series than 3D series. It is because they have higher enthalpy of atomization. It takes more energy to convert lattice into free atoms, and they are heavy transition metals. They have higher atomic mass, and they have strong metal bonding. Okay, actually there is one more trend. We saw information that the metallic bonding, I mean the melting point, generally increases at the middle of the series. At the middle of the series there will be highest melting point, but it's not completely true. It will increase till chromium, like in 3D series it will increase till chromium, but at manganese there will be a dip in the melting point, meaning there will be low melting point, a slightly less, or like there will be a big dip. This is because, like, the question is something like this: more number of unpaired electrons in manganese of 3D series, technetium of 4D series, and rhenium of 5D series. But their melting points are less. Why? Because we know that the configuration of in the middle of the series is, for example, manganese. If we take manganese has a configuration of 3d5 4s2. This is the configuration of manganese. Let me write it more clearly. Manganese has a configuration of 3d5 4s2. This is half filled configuration. Half filled configuration gives half filled stability, and because of this stability, this is in case of all of the technetium, rhenium, and manganese at the middle of the series. But I'm explaining specially to manganese because we know more about its electronic configuration than technetium and rhenium. 3d5 4s2. Because of this half filled stability, manganese, technetium, and rhenium have stable half filled d5 electronic configuration. Therefore, electrons are held more tightly by the nucleus. It does not want to give out electron and lose stability. It is already very stable, and it will not form intermolecular bonds to retain stability. Therefore, electrons are held more tightly by the nucleus, so delocalization of electrons is less, and hence metallic bonding is also less. This is why there is less intermetallic bonding, and this reduces the melting point, because even though they have the most number of unpaired electrons, their intermetallic bonding is less because they do not want to lose the half field stability by delocalizing the electrons. Okay, that is about the melting point. Coming to variation in atomic and ionic radius of elements, transition metals, variation of atomic radius, the atomic and ionic radii decreases with the increase in atomic number. This is a general trend. As we go from left of the periodic table to the right, the nuclear force increases and atomic radius decreases. And hence atomic radius generally decreases from left to right. In transition elements as well, this is generally the case. But this decrease in atomic radius from left to right generally becomes small after the halfway or the midway point. Example, if we take in 3D series, atomic radius decreases from scandium to chromium due to increase in effective nuclear charge, which is normal. But from chromium to copper, atomic radius remains almost same. This is because the increase in effective nuclear charge is compensated by the shielding effect or the screening effect. Zinc has larger atomic radius than copper due to completely filled orbitals and electron cloud expansion due to paired electrons. Okay, for example, I'll write the configuration, I mean the sizes, so we have a better understanding. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Now, scandium has a size of 164, titanium 147, vanadium 135, chromium 129, manganese 129, iron 128, cobalt 128, nickel 128, copper also 128. Zinc has 137. Okay, this is the configuration. If we see from chromium to copper, atomic size almost same, very similar. Why this happens? There are two reasons. Because of screening effect. Screening effect, the shielding of inner electrons, which reduces the effective nuclear charge on the outer electrons. This increases the size of the atom. Normally, as we go from left to right, these have like copper, cobalt, nickel, copper have higher nuclear charge than chromium and manganese or iron, but they have same radius because even though they have uh, higher positive charge, the inner electrons will repel the outer electrons. This is called as screening or shielding effect. Because of that, they will have to maintain a larger size than if there was no repulsion. Because of that, they will have the same size. But there is one exception here. Here, zinc has 137. And this shows that it has higher atomic radius than all of these. Why this is because zinc has larger atomic radius than copper due to it has completely filled d orbital, and because of the completely filled d orbital there will be electron cloud expansion. Because of paired electrons, this will increase the size of the zinc atom. Not much specific is needed for that. Just the main reason these will have same atomic radius is because screening effect. One more note point is here. As we go from left to right along the period of transition elements, density increases from left to right. Why? Because the atomic radius decreases due to effective nuclear charge, and more the number of electrons and protons are concentrated at a small space. Because of that, density increases automatically. Very simple. Okay, then variations in next topic is variations in ionization enthalpy. What is ionization enthalpy? The ionization enthalpy is the amount of energy required to ionize an element or an atom, or basically to remove the outermost electron from its gaseous atom, is known as ionization enthalpy. Ionization enthalpy of 3D series increases as we move across the period. Increases as we move across a period, as we move from left to right. This is due to increase in effective nuclear charge and filling of the inner d orbitals. And the second ionization enthalpy also the same. It increases as we move across a period from left to right. This is due to higher effective nuclear charge. But there it is not a regular trend. There will be irregularities and exceptions here. For example, exception is second ionization enthalpy, that is IE2 of chromium and copper are noticeably or sufficiently higher than their neighbors or neighboring elements. Because I can explain this. For example, configuration of chromium is 3d5 4s1. After first ionization enthalpy, it will be 3d5 4s0. Now this is a half filled configuration, half filled stability. Chromium plus 1 has a half filled stability. So IE2, which converts chromium plus to chromium 2 plus, which gives it configuration 3d4 4s0 from 3d5, which is losing stability, because chromium here it is half filled stability. There is half filled stability, half filled orbital stability gone. The same case for copper as well. In case of copper, it is fully filled stability. Copper, which has a configuration of 3d10 4s1, after IE1 it will be first ionization enthalpy will be 3d10 4s0. It is fully filled stability. Fully filled stability will be there, but after IE2 it will. Okay. We can see a special case in zinc. In zinc, if we take, actually it is in ionization enthalpy only, but still let's draw a line. A special case in zinc is that zinc ionization IE1 is higher compared to other atoms, other elements, because zinc configuration, if we take, it is 3d10 4s2. By doing ionization enthalpy, I mean by ionizing the atom, we are making 4s2 into 4s1. This is fully filled. Now this is not fully filled. Because of that, we are ruining the stability of zinc, and hence the first ionization enthalpy is higher than the neighboring atoms. In case of second ionization enthalpy of zinc, now this is different. This is lower compared to lower energy we need to provide to ionize this, lower compared to other atoms, because we have 3d10 4s1 configuration. By ionizing this atom, we are providing fully filled stability for the zinc 2 plus atom. It will become 4s0. This is fully filled, fully filled stability. Because of that, it is more, the zinc plus ion is more suited or more interested in becoming 3d10, which gives fully filled stability for it. So that is why less amount of energy we can provide, and we can make it 3d10 configuration. Then in case of, there is one more case, that is between manganese, which is 3d5 4s2, and iron, which is 3d6 4s2. Here the second the in this case, the ionization enthalpy also depends on half filled stability. The first ionization enthalpy will be similar, but the second ionization enthalpy of IE2 of manganese will be less than IE2 of iron. Less energy, because after the second electron is removed from manganese, it will have a half filled 3d5 configuration, which is highly stable. But in case of iron, this is not the case, as it will have a 3d6 configuration, which is not very stable. But IE3 of iron is much less than IE3 of manganese, because for iron, the third electron removed, it will be converted into stable half filled 3d5 configuration. But in case of manganese, we are ruining the 3d5 I mean the half filled stability here by removing a third electron. This will make it very unstable. Because of that, this energy is higher than the third one, which provides iron, third ionization enthalpy of iron, which provides it 3d5 stability. We are taking stability from manganese, we are adding stability to, we are not technically adding, we are adding energy, but it is more stable than other neighboring atoms. Then that's an exception. Now one more is ionization enthalpy of copper, nickel, and zinc is very high, and it is also difficult to, it is hence difficult to hard to see or obtain, it's more correct to say obtain, oxidation state greater than plus 2 for these elements. Their ionization enthalpy is very high. Because of that, it is hard to obtain oxidation state greater than plus 2 for these elements. So, after seeing all these exceptions, what can we conclude? What is the main reason for the varying in ionization enthalpy of the 3D series or the first transition series elements? It is mostly due to the varying electronic configuration, due to the irregular variation of ionization enthalpies, due to the varying degree of stability of different configuration. We are talking about electronic configurations. The varying ionization enthalpy is due to the varying degree of stability of different electronic configuration. Okay, that's about ionic enthalpies and oxidations. Now coming to oxidation states. In transition elements, there is a speciality here. In transition elements, they can show variable oxidation states. Normally in S block or P block elements, there is normally not many oxidation states possible. It is possible, but like it is not as versatile as transition elements, which have easier and more efficient way of showing higher and variable oxidation states. I can give an example by writing the common oxidation states shown by the 3D 3D series elements. Common oxidation state of 3D series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Scandium can only show plus 3, titanium can show plus 2, plus 3, and plus 4 configuration. Vanadium can show plus 2, plus 3, plus 4, and plus 5 configuration. Chromium can show all the way from plus 1, plus 2, plus 3, plus 4, plus 5, and even plus 6. Manganese can show plus 2, plus 3, plus 4, plus 5, plus 6, and plus 7. The highest oxidation state in 3D series is plus 7, shown by manganese. Iron can show plus 2, plus 3, plus 4, plus 5, and plus 6. Cobalt can show plus 2, plus 3, plus 4. Nickel can show plus 2, plus 3, and plus 4. Copper can show plus 1, plus 2, and zinc can show plus 2. I will round up the most common of these. Scandium has only one, so no need to specially round it up. Titanium will show plus 4, most common. Then vanadium will show plus 5. Chromium will show +3 and +6. If we talk about manganese, it is +2 and +7. Iron can show +2 and +3, the famous ferrous and ferric ions. Cobalt can show +2 and +3 as well. Nickel can show +2. We saw how nickel, copper, zinc, they are having very high ionization enthalpy, and hence it is uncommon for them to show oxidation states higher than +2. Copper is more prone to show +2, and zinc only +2 is there. So yes, that is it for the common oxidation state. Why are there variable oxidation states? The variable oxidation states of transition elements are due to the loss of inner n-1d and outer ns electrons. The minimum oxidation state is the loss of the ns electrons. The maximum oxidation state is the sum of loss of both n-1d unpaired electrons and ns electrons. The oxidation state increases as the atomic number increases up to manganese in 3D series and ruthenium in 4D series and osmium in 5D series. Then it decreases due to the pairing of electrons in d orbitals. It increases oxidation state increases up to manganese in 3D series, then ruthenium in 4D series, and osmium in 5D series, and then decreases due to pairing of electrons. Maximum oxidation state. In 3D series, manganese shows the maximum oxidation state of +7. Copper shows +1 oxidation states due to completely filled d orbitals. It is not common though. The oxidation state of nickel and ferrous in some complexes are 0 because for this we'll see more in coordination compounds chapter. Fe3 plus is more stable than Fe2 plus. Hence, Fe2 plus acts as a reducing agent. Okay, this is an important point. Fe3 plus is more stable than Fe2 plus. Hence, Fe2 plus acts as a reducing agent, meaning it will undergo oxidation to become Fe3 plus. Why so? It is D6 configuration. It is D5 half-filled configuration. And similarly, Cr3 plus is more stable than Cr2 plus. Hence, Cr2 plus acts as a reducing agent. Here, Cr2 plus configuration is 3D4 and Cr3 plus configuration is 3D3. Why 3D3 is more stable than 3D4? This also we will learn more in coordination compounds actually. It's because 3D3 in case of splitting of orbitals, the degenerate orbitals, they will have a splitting to form. In case of octahedral splitting, they will form 3 T2G orbitals and 2 EG orbitals. In such a case, the 3D3 configuration will have a half-filled T2G configuration, which will give half-filled stability, but 3D4 will not give half-filled stability. Because of that, 3D plus is more stable than CR3 plus is more stable than CR2 plus. Reducing agent means it will undergo oxidation. Then one more case is manganese 2 plus is more stable than manganese 3 plus. Hence, hence, let's write this first. Mn3 plus acts as a oxidizing agent, meaning it will undergo reduction to give this. Why so? Here Mn3 plus is 3D4 configuration, Mn2 plus is 3D5 configuration, 3D5 half-filled stability. So this will accept an electron, act as an oxidizing agent. An oxidizing agent, technically it is more correct to say an oxidizing agent does not accept an electron, it steals an electron, it snatches an electron from the other compound and hence acts as an oxidizing agent. It will help in the oxidation of the other compound by snatching an electron from it, and this oxidizing agent will itself undergo reduction and the compound other than the oxidizing agent will undergo oxidation. Then some important points. This is about oxidation state, and some important points are in 3D series, Mn shows highest oxidation state of 7 plus. In 4D series, ruthenium shows highest oxidation number of or highest oxidation state of 8 plus. In 5D series, osmium will show highest oxidation state of 8 plus again. Okay, there is a question. If we see here in scandium, why does scandium does not show +2 and +1 oxidation state or +2 oxidation state and only shows +3 oxidation state? Why? Because it is a speciality of why scandium exhibits 3D oxidation state, I mean +3 oxidation state. Scandium atomic number 21, configuration 3D14s2, argon 3D14s2. After scandium +3, it will show noble gas configuration. It will become 3D04s0. This is noble gas configuration. This is very highly stable. We already know noble gases are very stable. They are inert elements, and because scandium +3 has a noble gas configuration, it is also very stable, and hence instead of preferring scandium +2, which has 3d1, argon 3d1, it will prefer scandium plus 3, which is much more stable because of noble gas configuration. And element in 3D series which shows maximum highest oxidation state is manganese. It also shows the maximum number of oxidation state plus 2, plus 3, plus 4, plus 5, plus 6, and plus 7. Why it can do so is because it has the highest number of unpaired electrons and two 4s electrons. There is a famous question here. One more question. It is about why chromium 2 plus is a reducing agent and Mn3 plus is oxidizing agent when both have D4 configuration. This is because Mn manganese D4 configuration after why chromium is a reducing agent, or reducing agent means it itself undergoes oxidation. The configuration of Cr2 plus is 3d4. Cr3 plus it is 3d3. I told you this has half filled stability, half filled T2G stability. As for manganese plus 3 has a 3d4 configuration, plus 2 has a 3d5 configuration. This is half filled, again d orbital stability. And between Cr2 plus and Cr3 plus, Cr3 plus having half filled T2G stability is more stable. And between Mn3 plus and Mn2 plus, Mn plus 2 is more stable because of half filled d orbital stability. Because of that, Cr3 plus, I mean Cr2 plus will get converted into Cr3 plus. This is known as oxidation. Wait, yes, it's oxidation, so it will act as a reducing agent. And Mn3 plus will get converted into Mn2 plus. This is known as reduction, and hence it will act as an oxidizing agent. Okay. A note point, we saw many oxidation states in the table I wrote, but most of the oxidation state, the highest oxidation state, like plus 7 and all, highest oxidation state of a metal is only exhibited only in its oxide and fluoride or fluoride. This is the information. Why so? Because main reasons. First reason, it is both fluorine and oxygen are highly electronegative and small in size. This is the first reason. Okay. Fluorine has ability. Fluorine has ability to stabilize high oxidation state either because of higher lattice enthalpy, example in case of COF3, cobalt fluoride, it has higher lattice enthalpy or higher bond enthalpy between fluorine and its atom is very high. Example in case of vanadium fluoride or chromium fluoride. Now in case of oxygen, the ability of oxygen to stabilize higher oxidation states exceeds that of fluorine because of its ability to form multiple bonds, meaning double bonds. Single bond is weaker than a double bond. A double bond which is stronger than a single bond. Because of that, oxygen can form double bonds and it increases its stability. Example, magnesium highest magnesium fluoride is Mn4, but with oxygen is Mn2O7. Here the oxidation state is +4. Here it is +7. The structure of Mn2O7 is given here. Mn2O7, Mn double bond O, in Mn2O7, each Mn, that is manganese, is tetrahedrally led by oxygens, including a MnOMn bridge. This is a bridge, manganese oxygen manganese bridge. These are tetrahedral. Then we saw before, we explained how chromium and manganese are between chromium and manganese, which is a strong with a specific oxidation state, which is a stronger or weaker reducing agent or oxidizing agent based on electron configuration and its electron half bit stability. There is also one more way to explain which is a stronger reducing agent between two specific elements and their oxidation state. and that is by comparing their standard reduction potentials or oxidation potential. By comparing those, like, we can identify which is a stronger reducing agent or which is a weaker reducing agent or oxidizing agent or stronger oxidizing agent. There are two ways. One we saw is electron configuration, and second one is through the standard reduction SRP values. And one more important point regarding oxidation states is lower the oxidation state, of metal oxide, higher the metallic character. I mean ionic character. And inversely, higher the oxidation state of metal oxide, higher the covalent character. For example, in between magnesium 1 oxide and Mn2O7, which we saw before, which has higher ionic character, MnO will have the highest ionic character, whereas Mn2O7 will have the highest covalent character. There is a disproportionation of an oxidation state. The question is, what is disproportionation of an oxidation state? With an example. So we will see the example first. Here we have 3MnO4. Here plus 4 oxidation state for manganese, and plus 4H plus gives 2MnO4 minus. Here it is 2 minus. Here the oxidation state of manganese is plus 7 and plus MnO2. Here it is plus 4 again. Here it is not plus 4, it is plus 6. Plus 2H2O. Here a plus 6 oxidation state plus 6 plus 6 of manganese got converted into plus 7 here, and plus 6 got converted into plus 4 here. Here it is oxidation. Here it is reduction. Disproportionation reaction generally is a reaction where both oxidation and reduction of the same element happen at the same time. When a particular oxidation state becomes less stable relative to other oxidation state, one lower, one higher, it is said to undergo disproportionation. For example, manganese 6 becomes unstable relative to manganese 7 and manganese 4 in acidic solution. What they are saying is manganese plus 7 and manganese plus 4 are more stable comparatively than manganese plus 6. So in acidic medium, manganese plus 6 will undergo disproportionation to form a relatively higher stability products. Those are manganese plus 7 and manganese plus 4. Okay, one more important characteristic is Higher the oxidation state, higher the acidity. Higher the oxidation state, higher the acidity. Why so? Because normally acid can be defined as something which can accept electrons. So higher the oxidation state, higher the tendency of that specific metal to accept more number of electrons. So in case of an example given, if there are Cr2O3, CrO3 and CrO, we should arrange them in increasing order of their acidic character. First, let's write their oxidation state. Here it is +2, here it is +6, here it is 2x minus 6, which is equals to 0, it is +3. This oxidation state is for each chromium. So higher the oxidation state, higher the acidity. So least acid is the least oxidation state. So CrO more or less acidic than Cr2O3, less acidic than CrO3. Okay, there is one more very famous NCERT in text question here. Why is E naught, that is standard reduction potential value, from MM2 plus to metal of copper is positive, that is 0.34 volts, plus 0.34 volts? What is the reason for this? Why it is positive? Normally all the metallic character is to undergo reduction, I mean oxidation. Most of the metals will have, because they most of the metals prefer oxidation over reduction. Oxidation means loss of electrons to form positive cations. Reduction means to form accept electrons, and in this case to become neutral species. Why is it that copper's standard reduction potential from Mn2 plus to Mn positive? I mean not Mn, M, metal, M representing metal. Why is it positive? What could be the possible reason of this? The explanation given is that copper has high energy of atomization and low hydration enthalpy. The high energy to transform copper to copper 2 plus is not compensated by hydration enthalpy, hydration energy. So what is atomization energy or atomization enthalpy? The energy required to convert lattice into free atoms, that is atomization enthalpy. First, when we want to convert copper from lattice into hydration or like aqueous ions, this we will see in like electrochemistry Daniel cell, where the copper electrode will dissolve into the solution to become copper 2 plus. That is not the case. It's actually that won't happen in Daniel cell. The copper in the solution will only attached or is attached to the electrode. But an example in a reverse case scenario where copper will dissolve into the copper sulfate solution to become CO2 plus. In this, what happens is First, the copper in the metal is in the lattice form, and we need to provide energy of atomization to convert it into free atoms. These atoms need to be converted into aqueous form. For this, we need to provide, hydration enthalpy will be provided or liberated. But copper has, we need more energy to convert copper into atoms, free atoms. But the compensation for that, the energy liberated when copper from gaseous state is converted into aqueous state, this energy is known as hydration enthalpy. It's not enough to compensate the high energy of atomization. So the energy should be absorbed from surroundings, which is kind of a tedious process. So because of that, copper prefers copper as neutral state or ground state over copper 2 plus. Hence, E naught value of copper is positive. And one more point of information, scandium, E naught M3 plus to M2 plus is less. It does not prefer that. Why? Because M3 plus higher stability, because noble gas configuration, which I have explained before. One more is zinc has very high E naught M3 plus to M2 plus value, because at M3 plus it has 3D9 configuration, at M2 plus it has 310 configuration. Obviously 310 configuration is a fully filled orbital and it has higher stability. Because of that, zinc is more prone to be in 3D10 configuration than 3D9 configuration. Hence, it has a very high reduction potential. Okay, next is vanadium has low E naught, relatively low E naught, M3 plus to M2 plus value. Why? Vanadium configuration, if we write, vanadium atomic number is scandium, titanium, vanadium, Z, which is equals to scandium, titanium, vanadium 23. Now it is 3d3 4s2. In Mn3 plus it is 3d2 state. In Mn2 plus it is 3d3 state. 3d3. Why 3d3? That is vanadium 2 plus is more stable than vanadium 3 plus, is because at vanadium 3 plus it is half filled T2G configuration. Half filled T2G is more stable than 3D2. Because of that, next is E naught value of Mn3 plus. Actually, this is not needed, we already did this before. Okay. Okay, for example, if we saw this, like copper plus has a configuration of 310 4s0, and copper 2 plus is a configuration of 394s0. Here, this one, copper 2 plus, is a more common oxidation state or more stable oxidation state. Why? Even though copper plus has a fully filled 3d10 configuration, 3d9, that is Cu plus 2 of copper, is more stable oxidation state. Why do we say so? Why is that the case? We can explain this by, since we are not able to understand this using electron configuration, we can explain this using SRP values, standard electrode reduction potential values. If we see Cu plus to Cu, this E naught value is 0.52 volt, very favorable. But Cu2 plus to Cu, this E naught value, it is 0.34 volt, not as favorable. So in comparatively, Cu to Cu plus to Cu is more stable than Cu plus. Like this reaction is favored, more favored. But this reaction isn't so favored because the value is slightly less. So we can say that Cu2 plus is more stable than Cu plus. Cu2 plus is more stable than Cu plus, or we can understand this from like stability of definition. The relative stability of cations can be explained on the basis of their standard electrode potential. The stability of ion inversely proportional to the E naught value. Higher the E naught value, lesser its stability. Stability of ion, we are specifically talking about the cation or ion, not about the ground state, is directly proportional to the, inversely proportional to the E naught values. Higher the E naught, lesser the stability of the ion. So here this value is very high, so stability of Cu plus is more, less, Cu is more. Here it is less, slightly less, so comparatively this is also less and this is only more, but still compared to these both, Cu2 plus will have a higher stability. Hence Cu2 plus is a more common or more stable oxidation state. This is important relation. They gave an example here. Oxidizing power. Oxidizing power VO2 plus Cr2O7 2 plus and MnO4 minus. MnO4 minus has the highest oxidizing power, then VO2 plus has the least. Why is this? So how do you account for the increasing oxidizing power in the series? Meaning they have high oxidizing power, so that means they are supposed to get reduced This is due to increasing stability of the lower species which they are reduced. In here, if we write the oxidation states, VO2 plus vanadium X minus 2, which is equals to plus 2, so cancel. Here it seems vanadium has a 0 oxidation state. Chromium plus 2 if we take, then 2x which is plus mean minus 14 which is equals to 2. Here it is plus 6 oxidation state. Plus 6 oxidation state. And here in case of manganese it is x minus 8 which is equals to minus 1, so plus 7 oxidation state. Highest oxidation state is manganese. Highest oxidizing power means highest reducing agent. Strongest oxidizing power means like highest oxidizing agent. So this means they should have highest they should be able to get reduced easily. Mn plus 4 can easily get reduced because it has the highest oxidation number and it can show highest acidity and easily accept electrons, and this goes on decreasing as the oxidation number decreases. Okay, one more reason. Okay, this one we can go to the next question. NCERT in text question. Copper plus is less stable than Cu2 plus in aqueous solution. Hence, it will go a disproportionation to give Cu2 plus and Cu. Why reason? One more reason is more negative enthalpy of more negative enthalpy for hydration of Cu2 plus ion than Cu plus ion, which is more than second ionization enthalpy of copper. Here we saw before why copper 2 plus has a positive 0.34 electron standard reduction potential, because we saw that higher atomization enthalpy, its atomization enthalpy for copper is very high, but the hydration compensation which is receiving when copper gaseous is converted into aqueous is less than needed, less than supplied. So because of that we saw it has positive uh, reduction potential. Here comparatively, comparing the same hydration, negative hydration enthalpy, copper 2 plus has higher hydration enthalpy than copper plus. Because of that, it is more stable than copper plus in aqueous solution. Just that it releases copper 2 plus will release more energy than copper plus when it is dissolved in the aqueous solution. That itself is the idea of hydration enthalpy. Now coming to the next topic, magnetic properties. Magnetic properties of transition metals. Simply, they can be explained as If unpaired electron present, then paramagnetic. If unpaired electron not present, then diamagnetic. These are the two magnetic properties of transition metals. Most of the transition metals and their compounds are paramagnetic, slightly attracted by magnet. Paramagnetic means slightly attracted by magnet. Diamagnetic meaning slightly repelled by magnet. The magnetic magnetism is due to the presence of unpaired electrons in the d orbitals. The main cause of paramagnetism are orbital angular momentum and spin momentum of the electron. Important points: most transition metals paramagnetic, they have unpaired electrons. Paramagnetism due to one, orbital angular momentum, two, spin angular momentum of electron here as well, here as well of electron, orbital angular momentum of electron and spin angular momentum of electron. The formula to calculate the magnetic momentum is spin only formula. We will only consider the spin. Orbital angular momentum, which is the whole orbit or the whole revolution of electron around the nucleus, is not considered. The electron will be, actually electron has a charge. Why this paramagnetism is caused? Because first, on orbital angular momentum, we know that the electrons will be revolving around the nucleus, and because of the revolving around the nucleus, electron has a charge, and moving charge produces magnetic fields, and because of that, orbital angular momentum will be there. But we do not care about that. It is negligible, very less. So the only thing we care about is spin angular momentum of electron. The electron will be revolving around itself. When it is unpaired, there will be a non-negligible amount of magnetic field produced by the electron due to its spin, a characteristic of its spin of electron. And to calculate the spin only the magnetic moment of electron due to only its spin, so that is why the formula is spin only formula. That is mu, which is basically magnetic moment, which is equals to root of n into n plus 2 Bohr magneton. Bohr magneton is the unit of the magnetic moment, spelled like this, where n is the number of unpaired electrons. This formula is very, very important. The magnetic moment increases as the number of unpaired electrons increases. Now coming to diamagnetic substances, the substances which are repelled or not attracted by an applied magnetic field due to the absence of unpaired electron are called diamagnetic substances. Examples are completely filled orbitals like zinc, zinc 2 plus, scandium 3 plus, titanium 4 plus. copper 2 plus, etc. are diamagnetic due to the absence of unpaired electrons. Let's see a simple question. Among zinc 2 plus and cobalt 3 plus, which is not attracted by a magnet? Zinc 2 plus configuration 3d10 4s0. Obviously, this is not attracted by a magnet because it is diamagnetic in nature, because it does not have unpaired electrons. In case of cobalt 3 plus, it has unpaired electrons, so it is attracted by magnet. Attracted by magnet, not attracted by magnet. So zinc 2 plus is the answer. This same question can be answered in another way. Among zinc salts and cobalt salts, which are not attracted by magnet, zinc salts meaning zinc will have a plus 2 configuration and cobalt will have a plus 3 configuration or plus 2 configuration. Zinc plus 2 or 0, both the states are diamagnetic in nature, so because of that, zinc salts will not be attracted by the magnet. They will be slightly repelled. There's a formula to find the number of, I mean, oxidation state of, number of unpaired electrons in an atom. Number of unpaired electrons, n, which is equals to Z, atomic number, minus oxidation state, minus atomic number of Z of the nearest noble gas or noble gas in their series. For example, in 3D series, it is the atomic number of argon. For example, if we do an example, titanium 3 plus, number of electrons titanium, it is 22, oxidation state 3, minus 18 is the atomic number of argon, 1 unpaired electron. And we can calculate magnetic moment by substituting in the formula. Nu is equals to root of n into n plus 2 Bohr magneton, mu which is equals to root of 1 into 1 plus 2 is equals to root 3 or 1.7 Bohr magneton, approximately 1.7 Bohr magneton. Okay, right. That's how we should calculate the magnetic moment. Then one more important point is, or question is, how is there color in explanation of color of transition metal ions? They produce color because presence of unpaired electron in d orbital. DD transitions. The d electrons absorb color from visible region and undergo DD transitions and radiate complementary colors. Example, Cu2 plus absorbs red and emits blue light. Hence, the copper sulfate solution is blue in nature, sky blue color. Complementary color to red is blue. Zinc salts are colorless. Zinc 2 plus salts are colorless because it has no unpaired electrons. Copper 2 plus salts are color, presence of unpaired electrons. Cobalt salts are colored. Scandium 3 plus salts are not colored. Zinc 2 plus salts are not colored. Chromium 3 plus salts are colored. Copper 1 salts are colorless because it has 3D10 configuration, but copper 2 salts are colored. Zinc, it is colorless in both ground or atomic state and oxidation state. There is an important question. Reason transition metals form large number of complex compounds or coordination compounds. Complex compounds. Reasons: smaller size of transition metals, the central metal atom, larger ionic charges, or basically high polarizing power. Meaning high charge to size ratio, meaning they have smaller size, meaning more ligands can get attracted and be closely associated with the central metal atom, and they have high positive charge, meaning they can easily attract the negative charge of the ligands. That is a high polarizing power. And they have vacant d orbitals. Two of the points depend on the size and uh, positive charge. Third point depends on the main thing, availability of d orbitals. Availability of, they can provide, the central metal atom, that is the transition metals, can provide vacant, sufficient number of vacant d orbitals. As many as the ligand wants, it can provide. and hence they are also colored. They can spend vacant d orbitals to form bonds. This is coordinate bonds. They will accept the electron pair from the ligand into the d orbitals. We will see this more in our next chapter, coordination compounds, which I will be covering in the same video. Okay, one more important property of transition metals is catalytic property of transition metals. Catalytic meaning they can act as catalyst. What is a catalyst? A catalyst is a substance which is used in a chemical reaction which does not necessarily take part in the reaction and does not influence the product of the reaction but increases the rate of the reaction. Catalysts do not directly or necessarily involve in the reaction. They increase the rate of the reaction. They do not change the product, and they are reproduced after the reaction. Why they are catalytic? They have catalytic properties. They behave as catalysts because they have variable transition metal of transition metal. They can behave as catalyst because they have variable oxidation state. Large surface area metals are solid, so they can provide large surface area for adsorption of reactant molecules. Presence of incompletely filled or partially filled d orbitals. Then formation of intermediate compounds. What this means is the if there is a reactant adsorbed or like present on the surface of the catalyst that is a metal will form metal reactant bonds. This will weaken the interatomic bonds of the reactant, and this will reduce the bond enthalpy of the reactant, and it can easily break apart in a reaction. These are intermediate bonds. The catalyst does not directly take part in the reaction. It will just form bonds to help reducing the bond enthalpy between the reactant molecules. This is called as formation of intermediate compounds. The adsorption and not absorption is the reason it forms bonds. Examples for catalysts are very, very important. Vanadium pentoxide V2O5 used in contact process, that is manufacture of H2SO4, which we will see in p block elements, but I think I won't be covering p block elements in this video. I will see you when to do that later. V2O5 contact process, manufacture of sulfuric acid. Then we have Fe2O3, that is iron oxide. It is used in Haber's process, a very, very famous process. This is for the manufacture of NH3 ammonia. Then nickel used in hydrogenation of oils. The reaction, general reaction is oils plus H2 in presence of nickel give fats. Then we have many other catalysts like titanium chloride or titanium in Baker's process, I believe. I'll check that later. Okay, one more important question is about interstitial compounds. Interstitial compounds, compounds in which small atoms like hydrogen, carbon, or nitrogen are trapped into the cavities or empty spaces of crystal lattice of metals. Compounds in which small atoms like hydrogen, carbon, or nitrogen are trapped into the cavities of crystal lattice of metals. Basically, the metals are in the form of lattice structures. Lattice structures will have some cavities in them. In these cavities, when some compounds are trapped, these compounds change the properties of physical properties of the metal in which they are trapped due to formation of metal and non-metal bonds. These are non-metals, so they will form metal non-metal bond, and it will change the properties of the metals. How they change we will see. And this formation or these specific compounds which have non-metals trapped inside them are known as interstitial compounds. Example, we have titanium carbon. It's not very correct stoichiometric ratio, as the correct exact ratios is not very measurable. Mn4C, Fp3H, VH 0.56, and titanium hydrogen 1.7, etc. The physical and chemical properties are, these are non-stoichiometric, not exactly correct. High melting and higher melting point than original pure metals. Why this is the case? Because I told that these non-metals which are trapped inside the cavities of the metal lattice will form non-metal and metal bonds with the intermolecular metal atoms. Metal non-metal bonds will be formed. This will strengthen the intermolecular bond strength, or like attraction will be increased. Because of this, the melting point will also be increased. Very hard. Some borides are as hard as diamond. Are as hard as diamond. They are chemically inert. Chemically inert meaning they are not very reactive, maybe because they already have the metal non-metal bond which they have donated the electrons, and most of the electrons are already delocalized. This could be a reason they are chemically inert. They are metallic, they retain metallic conductivity, they are conductive. Same as originals, conductive in nature. The cavity which we talked about in the interstitial compounds where these nonmetals get trapped, these are either called cavities, they can be called interstitial spaces, or voids. Cavities, interstitial spaces, or voids. Okay, then there is one more physical property about alloy formation. Transition elements have strong tendency to form alloys. To form alloys. Because their atomic sizes are very similar. We talked about why they are similar in example of from manganese to copper, where the atomic size was very similar due to the screening effect. Main reasons is similar atomic size. And in the crystal lattice, one metal can be readily replaced by another. Like there will be a crystal lattice structure in that, because the sizes and properties are almost very similar, one metal atom can be replaced by another metal atom. There won't be any much difference, due to which there is not much difference between the physical properties of the metals, and they can form alloys. Properties of the alloys are hard and have high melting point. Examples are stainless steel, which is an alloy of iron, carbon, chromium, and nickel. Then amalgam is an alloy of mercury with any specific metal with another metal like sodium amalgam, iron amalgam, etc. Any other metal. Mercury with any other metal. Then two important examples to be remembered: brass, which is copper plus zinc, and bronze, copper plus tin. Let's use the atomic name itself, atomic symbol. This is tin. Where this is very confusing to remember, so you can remember them as reverse of what they are. Where there is Z, there will not be zinc. Here there will be zinc cross. Where there will be S, there will be there will not be tin, and there will be a cross here. Brass, there is an S, so it is copper plus zinc. Bronze, there is a Z, so copper plus tin. Now let's take a brief 5 minutes break. Okay, then let's continue. Okay, we are going to start with the next topic, that is some important compounds in transition elements, or some compounds or some important compounds of transition elements. The first question under this topic is characteristics of oxides and oxanions of transition elements. Characteristics of oxides and oxanions of transition metals. They are all transition metals except scandium form metal oxides which are ionic and basic in nature. Scandium maybe cannot form because its initial oxidation state itself is +3, and higher the oxidation state, higher the covalent character, so it cannot maybe form ionic and basic nature. Then higher oxidation states, oxides like Mn2O7 are covalent and acidic in nature. Higher the oxidation number, higher the covalency, and higher the oxidation number, higher the acidity. Then this is the most important point. Some metal oxides react with both acids and bases. Such oxides are called amphoteric oxides. Oxides which react with both acids and bases are called as amphoteric oxides. Examples are again very, very important. Examples are chromium oxide, oops, Cr2O3, chromium oxide, vanadium pentoxide, V2O5, used in contact process. Okay, why vanadium oxide is a amphoteric oxide? Because it reacts with both alkalis and acids like V2O5 plus alkali basic nature will give VO4 3 minus, and V2O5 plus acid will give VO4 plus. Here the oxidation state of vanadium is +5, here as well +5. In this case it is also +5. In this case, it is plus 7 x minus 8 plus 9 it seems, but that not might be true. I'll check it later. Cannot be plus 9 as the highest itself was plus 7. Anyways, we don't need to care about the oxidation state. We just need to know that vanadium pentoxide will react with base and acid to give these specific compounds or molecules. As such, it is amphoteric oxide. As for Cr2O3, I think some important points are given. Let's just write them once. Oxidation number directly proportional to covalent character and acidic nature. Higher the oxidation number, higher the covalent character and higher the acidity. Oxidation number inversely proportional to ionic and basic nature. Higher the lower the oxidation number, higher the ionic nature, higher the basic nature. From left to right, of a periodic table, generally ionic character and basic nature decrease and covalent character and acidic character increase. This is actually a general rule. As we go from left to right, we move from S block side to P block side. P block side are more acidic, more covalent compared to S block, which are metals, which are the most electropositive. Electronegativity increases from left to right. Electropositivity decreases from left to right. Electronegativity increases from top to bottom. Decreases from top to bottom. Electropositivity increases from top to bottom. These are the general trends of electropositivity and negativity. For example of this, in case of acidic character acidity, titanium oxide less acidic than vanadium oxide, less acidic than chromium oxide, less acidic than manganese oxide, and so on. This is because as we move from left to right, acidity increases. Acidic character of the metal oxide increases. On the leftmost side, most basic, least acidic metallic oxides are seen. Then some properties of some compounds are given. Mn2O7, which we saw was a tetrahedral structure, two tetrahedral structures combined via MnO-Mn bridge. What is this? Is a green oil, and it gives HMNO4 permanganic acid in aqueous solution that shows its acidic character. This it gives permanganic acid in aqueous solution showing its acidic character. Permanganic acid is acidic in nature, and since this is giving acidic compound permanganic acid in aqueous solution, it shows that it is acidic in nature. Why it is acidic in nature? HMnO4, it can easily donate H plus, so that is why it is acidic in nature. And coming to CrO3, I mean Cr2O3, no, it's CrO3 only. CrO3 gives H2CrO4 and donate 2 hydrogen plus, and H2Cr2O7 showing acidic in nature, showing its acid nature in aqueous solution. Why these are acidic? Because presence of H2 and H here, which can easily liberate them and become H plus. Donation of proton is acidity. Acids donate hydrogen, accept electron. This is the character of acids. Bases donate OH minus or accept H plus or accept electron. This is the nature of bases. V2O5 is amphoteric. Vanadium pentoxide is amphoteric in nature. CrO is basic in nature, whereas Cr2O3, which is a higher oxide, is amphoteric in nature. If there is an even higher oxide, that would be acidic in nature. Uh, then coming to a MCQ possible question. What is the important ore or chief ore of potassium dichromate? Chief ore of potassium dichromate, from where it is produced from, it is called as chromite ore or chromite ironstone. Its formula is FeO dot Cr2O3 or FeCr2O4. This is the formula. FeOCr2O4 or 3 or FeC2Cr2O4. Chromite ore. This is the main ore to produce potassium dichromate. Potassium dichromate. Now, uses of potassium dichromate. This is not a G, this is Cr2O7. Used in leather industry, the leather which is used in shoes, belts, etc. Manufactured normally from animal skin. Used as an oxidizing agent. Why? If we see K2Cr2O7, it is basically Cr2O7 2 minus, in here 2x minus 14, which is equals to minus 2, And here oxidation state of chromium is, from this we can say it is plus 6. Plus 6 is the oxidation state of, plus 6 is the oxidation state of, plus 6 is the oxidation state of chromium. In such a case, it has a very high oxidation state. It can act as an oxidizing agent, meaning it can undergo reduction and help in the oxidation of other reagents, and hence it acts as an oxidizing agent. Because it has a higher oxidation state, it acts as an oxidizing agent. It will undergo reduction, it will become a more stable product. Then one more use in quantitative analysis as a primary standard. It is used in quantitative analysis as a primary standard, very useful in quantitative analysis. It is also used in qualitative analysis, salt analysis basically, qualitative. So we can say in a single line it is used in both quantitative and qualitative analysis. For qualitative, for chloride ion test. Okay, the next is one of the most important question of the board exams of class 12th. Process of manufacture of K2Cr2O7. Process of manufacture of potassium dichromate. Step 1, chromite ore is heated with sodium carbonate in excess air to form sodium chromate. The reaction is something like this: 4FeCr2O4 plus 8Na2CrO3 plus, it is CO3, not CrO3, sodium carbonate, Na2CO3 plus 7 oxygen gives 8Na2CrO4 sodium chromate plus 2Fe2O3 ferric oxide plus 8 CO2. First step. Step 2, yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give orange solution of sodium dichromate. something wrong here, plus H2. Okay, then step 3, final step, solution of sodium dichromate, orange solution, treated with KCl for a displacement reaction to form potassium dichromate. 2Na2, Na2 Cr2O7 plus KCl gives K2Cr2O7 or potassium dichromate plus 2NaCl. Let's just review it once more. Step 1, chromate ore is heated with sodium carbonate in excess air to form sodium chromate. We have chromate ore here. We take sodium carbonate in excess air. We heat it. We get sodium chromate, ferric oxide and carbon dioxide. This is a yellow solution of sodium chromate. It's filtered and acidified with sulfuric acid to give orange solution of sodium dichromate. Basically, there will be chromate here, single chromate. It will be acidified in presence of sulfuric acid to give sodium dichromate. 2Na plus will be extra and H2O. This is called filtration step and acidification step. Final step is displacement reaction. This sodium dichromate solution, which is the orange in color, is treated with KCl to form potassium dichromate. Basically we add KCl, to KCl, two potassium ions from KCl will replace two sodium ions. It will become potassium dichromate and NaCl will be a byproduct. That is the process of manufacture. Now another important question which is not usually paired up here is structure of chromate ion and dichromate ion. Structure of chromate and dichromate ion. It will be tetrahedral in structure, chromate ion, CRO. There will be a thick bond here, O, and a dash bond. This is the chromate ion. As for dichromate ion, this angle is 126 degree. The bond length is 179 picometer. This is dichromate. Both have essentially the same charge, that is 2 minus 207, 2 minus. There is a bridging carbon here. Now reactions of potassium dichromate are important as well. The main use in this reaction is K2Cr2O7. This strong oxidizing agent. How does it react with first one? It is iodine. Oxidizing agent meaning it will help the other get oxidized. So iodine, which has a -1 oxidation number, will get oxidized to form iodide. Wait, iodine. This is iodide and this is iodine. Here it is, oxidation number is 0. So this should be facilitated by potassium dichromate. In presence of acid, the action of potassium dichromate can be written as Cr2O7 2 minus react with 14H plus and 6 electron to give Cr3 plus and 7H2O. Here oxidation number of Cr is +6. Here it is +3, so it is reduction. It will undergo reduction and help in oxidation. Okay, the first reaction, oxidation of iodide to iodine. K2Cr2O7 oxidizes iodide to iodine. The reaction in acidified. So we take the above reaction Cr2O7 2 minus plus 14H plus 6 electrons gives 2Cr3 plus 7H2O. This is the acidification reaction of the potassium dichromate. Now, since we are taking 6 electrons, we need 6 electrons, so we take 6 iodide ions, gives 3I2 plus 6 electron. Now we add them both. 6 electron on both sides get cancelled. So it will be 6I minus plus Cr2O7 2 minus plus 14H plus gives 2Cr3 plus 3 iodine plus 7H2. This is the reaction, total sum reaction. Now let's see how it oxidizes iron. The main reaction that should be remembered is Cr2O7, that is potassium dichromate, plus 14H plus 6 electron gives 2 chromium 3 plus 7H2O. This is the main reaction that needs to be remembered. Now the second reaction is Fe2 plus, that is ferrous, if oxidized to ferric. Now the same reaction for acidified potassium dichromate, that is Cr2O7 2 minus plus 14H plus 6 electron gives 2 Cr3 plus I think 7H2O. Yeah, 7H2O. As for ferrous to ferric, it is, since we need to provide 6 electron, 6 Fe2 plus converts into 6 Fe3 plus 6 electron. The sum total of the reaction, 6 electron get cancelled. Cr2O7 2 minus plus 6 Fe2 plus 14H plus gives 2 Cr3 plus 6 Fe3 plus 7H2. This is the final reaction. Now third one, tin 2 plus, oxidation of tin 2 plus to tin 4 plus salt, that is tin 2 plus is called stannous, whereas tin 4 plus stannic. Stannous salts to stannic salts. Again the same reaction for acidified potassium dichromate, Cr2O7 2 minus plus 14H plus 6 electron gives Cr2 no Cr 2Cr plus 3 plus 7H2. Now stannous to stannic, since 2 electrons are being provided, we take 3 stannous 2 plus gets converted into 3 stannous 3 4 plus 6 electrons, 6 electron get cancelled. Final reaction, Cr2O7 2 minus 2 minus plus 14H plus 3SN2 plus gives 3SN4 plus 2Cr2 plus, 3 plus 7H2. This is the final reaction. There seems to be some glitching happening. And next it is oxidation of hydrogen sulfide H2S, which can be oxidized to give H2S. Here the oxidation state of sulfur, it is -2, and for each hydrogen it is +1. It can be oxidized to give sulfur and 2 hydrogen, 2H plus. Here it is 0, it is still +1. Now it is written as it oxidizes H2S to pale yellow precipitate of sulfur. To pale yellow precipitate of sulfur. Now the same reaction for potassium acidified potassium dichromate, Cr2O7 2 minus plus 14H plus 6 electron gives Cr plus 3 2 plus 7H2. And for hydrogen sulfide, since we need uh, since we need 6 electron, we'll take 3H2S. This will give 6H plus 3 sulfur and 6 electrons. If we cancel electrons, it will be Cr2O7 2 minus plus 14H plus 3H2S 2Cr plus 3 plus 6H plus 7H2. Okay, that's about the reactions of potassium dichromate. We can explain interconversion of chromates and dichromate ions depending on pH. This is step is chromate, that is CrO4 2 minus, converted into Cr2O7 2 minus in acidic medium. Cr2O7 2 minus will get converted into CrO4 2 minus in basic medium. The reaction is something like this. Cr2O7 2 minus, which is orange and red, plus H2O, that is like OH minus 2CrO4 2 minus plus 2H plus. This is yellow in color. Now one more important question, which is like very important for board exams, that is, how is potash, or like there is no need for how is, just let's write manufacture of potassium permanganate that is KMnO4. It is manufactured using pyrolusite ore, that is pyrolusite is MnO2. Step 1, pyrolusite is powdered and fused with KOH, potassium hydroxide, in presence of KNO3 as an oxidizing agent to form potassium manganate, not permanganate, potassium manganate. The chemical reaction is pyrolusite, it is powdered and fused with KOH in presence of KNO3 acting as an oxidizing agent. KNO3 acting as an oxidizing agent to form 2K2MnO4. This is K2MnO4 is potassium manganate and 2H2O. Only two steps in this reaction. Step 2, green colored potassium manganate undergoes disproportionation in acidic. In acidic, it is important to remember the medium here. Green colored, it is important to remember the color as well. Potassium manganate undergoes disproportionation in acidic or neutral medium, can be acidic or neutral medium. And the reaction is also important to give disproportionation reaction to give potassium permanganate, KMnO4. Okay, there is something wrong with this. To give KMnO4. Now the reaction is 3MnO4 minus 2 minus. This is manganate plus 4H plus in acidic medium. 2MnO4 minus, this is permanganate, plus MnO2 plus 2H2. Here the oxidation state of manganate, permanganate, here it is like, let's see here first. It is X minus 8, which is equals to minus 2. So it is plus 6 here. Then here it is plus 7. And here in case of pyrolusite it is plus 4. So it plus 6 got converted into plus 7 and plus 4. This is disproportionation reaction. I'll check the issue later. That is the step. The purple solution obtained is concentrated to get dark purple crystals of KMnO4. Note, there is one more reaction for like commercial purpose. Commercially, permanganate ion is obtained by electrolytic oxidation of manganate ion in alkaline medium. Okay, this is new here. In previous, we saw that the permanganate ion was obtained by uh, manganate ion undergoes disproportionation in acidic or neutral medium. But in commercially, it is because maybe the disproportionation reaction in acidic or neutral may be slow. Because of that, commercially, permanganate ion is obtained by electrolytic oxidation. Here it is in alkaline medium. In alkaline medium, it is oxidized. Why oxidation? If we see the reaction here, uh, +6, +7, and +4. Here the oxidation states are +6 and +7, +4. Disproportionate. +6 becomes +7, and plus as +6 also becomes +4. Disproportionation reaction. Because of that, for our main product is Mn permanganate. That means that this needs to be oxidized. We know we don't need this MnO2. Our main product is permanganate, so we need, the only thing we need is the oxidation of this to get our permanganate. Oxidation of manganate to give permanganate. If we get that, that much is enough for us. So that is the reason alkaline medium oxidation is done. Commercial. The general equation MnO2 fused with KOH oxidized with air or KNO3 to give MnO4 2 minus manganate ion and electrolytic oxidation in alkaline medium to give MnO4 minus permanganate. This is our final product. There is also one more preparation for potassium permanganate. It is not very important as for board, but as for competitive, it is good to know this one. It is laboratory preparation of KMnO4 potassium permanganate. Why laboratory preparation needs to be separate or different from normal preparation? Because like laboratory is a small scale, we need only small amount of KMnO4, and the apparatus we needed for large scale production is not available in the laboratory generally. So we need to go with a simpler method. Okay, in laboratory, KMnO4 is obtained by oxidation of a manganese KMnO4 is obtained by oxidation of a manganese to ion salt by peroxodisulfate. That is the reaction is 2Mn2 plus. There is a salt ion from salt, peroxodisulfate, 2 minus 5S2O8, 2 minus plus 8H2O gives 2MnO4 minus plus 8SO4 2 minus plus 16H plus manganese 2 plus manganese 2 plus will react with peroxodisulfate S2O8 and water to give 2MnO4 minus, that is our permanganate, and sulfate ion, 8 sulfates and 16H plus. Then one more question that can be asked is structure of, based on structure of the MnO4 minus and MnO4 2 minus. Mn manganate ion tetrahedral this is permanganate ion. This is also tetrahedral structure. Then there is a specific reaction of what will happen if we heat action on potassium dichromate, I mean potassium permanganate. KMnO4 on heating to 513 Kelvin. They undergo disproportionation to give potassium manganate and MnO2 plus O2. On heating, okay, anyways, okay, on heating, KMnO4, that is potassium permanganate, it will give on heating to 513 Kelvin, it will give K2MnO4, that is manganate, MnO2 and O2. Okay, again reactions with potassium manganate. We see the oxidation number of here, it is +7. So that means it is a strong oxidizing agent. KMnO4 is a strong oxidizing agent. In acidic solution, okay, note point is KMnO4, potassium permanganate, is strong oxidizing agent in acidic, basic and neutral mediums. It is in all mediums, it is oxidizing agent, strong oxidizing agent. The reaction can be written as MnO4 minus plus 8H plus 5 electrons gives Mn2 plus 4H2O. For example, I minus to iodine, iodide to iodine. The reaction is first our acidic medium reaction, MnO4 minus 8H plus 5 electron oxidizes it to Mn2 plus from +7 to +2 and 4H2O is liberated. Now, since we need 5 electrons, and it's an odd number, we need to take this 2 times into 2, and iodine, iodide, 2 iodide gets oxidized to give iodine plus 2 electrons. This we need to do it 5 times. Just a minute. Okay, let's continue. The total reaction, actually let's write the reactions again, since we need to multiply it two times. For odd number equations, this is a problem. 2MnO4 minus plus 16H plus 10 electron gives 2Mn2 plus 8H2O. Then we have 10 iodine minus gives 5I2 plus 10 electrons. We need to add these equations. 10 electron cancel. Then we'll get 2MnO4 minus plus 16H plus 10 iodide gives 2Mn2 plus 8H2O plus 5I2. Then we have one more reaction. 2 oxidizes KMnO4 permanganate oxidize Fp2 plus green color to Fp3 plus ferrous to ferric yellow color. We know the permanganate reaction MnO4 2 minus, MnO4 minus. Fp plus 2 green to Fp plus 3 ferrous to ferric yellow. Then we know MnO4 minus plus 8H plus 5 electron gives MnO4, no wait, plus 8H plus 5 electrons Okay, I created a new page, new blank document this time. Hope there won't be much error this time. Okay, second one, ferrous to ferric. This is green color to ferric plus 3 yellow. The main reaction of permanganate MnO4 minus plus 8H plus 5 electron gives MnO2 plus I think 4H2O is 4H2. Now we need 5 electrons, so 5Fe plus 2 gives 5Fe plus 3 plus 5 electrons. We can cancel 5 electrons. MnO4 minus plus 8H plus 5 Fe plus 2 gives Mn plus 2 plus 4H2O plus 5Fe plus 3. This is the final reaction. Then there is oxalate ion or oxalic acid is oxidized to CO2 carbon dioxide at 333 Kelvin by permanganate. Permanganate reaction is normal. MnO4 2 1 minus 8H plus 5 electron gives Mn plus 2 plus 8H2O 4H2O 4H2O and oxalate to oxalic acid. Oxalate is C2O4 2 minus 2 2CO2 plus 2 electron. Here the oxidation state is 2x minus 8, which is equals to minus 2. So it is plus 3 each carbon. Here it is plus 4. Yes, plus 4 is oxidation state. So clearly it is oxidation reaction. Now since it's 2 electrons, multiply this equation by 2 and this equation by 5, then we will get 2MnO4 minus plus 16H plus 10 electrons gives 4 no, 2Mn2 plus 8H2 and oxalic acid reaction C2O4 2 minus gives 10 CO2 plus 10 electrons. 10 electrons cancel. 2MnO4 minus plus 16H plus 5C2O4 2 minus gives 2Mn2 plus 8H2O plus 10 carbon dioxide. That is the whole reaction. Now we can do next one, hydrogen sulfide, H2S oxidized to yellow precipitate of sulfur. Now MnO4 reaction we know, MnO4 2 minus plus 8H plus 5 electrons, Mn2 plus 4H2. Now the reaction of H2S is H2S plus 2H plus S plus 2 electrons. Now again we need to multiply this by 2, this by 5. We will get 2MnO4 minus plus 16H plus 10 electrons gives 2Mn plus 2 plus 8H2O, 5H2S, 10H plus 5 sulfur plus 10 electrons. Whole reaction 2MnO4 minus plus 16H plus 5H2S gives 2Mn plus 2 plus 10H plus 5 electrons, 5 sulfur plus 8H2O. We can cancel 10H plus 10H plus from both sides. That is that one. Then there is one more.